For this worksheet, I'm going to do this answer key rather than giving specific notes for points on your worksheet. So for the following compounds, we need to name these compounds. So in this case, for the first structure, we have a cyclohexane ring, and I'm going to start numbering the carbons. And I'm going to go ahead and pick a carbon with a substituent, just so that hopefully it matches up with what the numbers should relate to in terms of where the substituents are attached. So we've got carbon 1, 2, 3, 4, and 5, 6. And it looks like we have a methyl group at carbon number 1 and at carbon number 3. So definitely this was a good place to start. So when we're naming them, we've got 2 methyl groups. So this is 1, 3, dimethyl cyclohexane. For the second one, we've got 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. So this is pentane. For the next, we also have 5 carbons, but we have a methyl group on carbon number 2. So 1, 2, 3, 4, 5. So this is 2 methyl pentane. And for the next one, I'm going to start on this end because it looks like we have an ethyl substituent right there. So we'll say carbon number 1, 2, 3. We've got a bromine on 4. And 5, 6, 7. So this is heptane. So 3 ethyl, 4 bromo heptane. Bromo comes first, so it's going to be alphabetically. So it's 4 bromo, 3 ethyl heptane. All right, for the next one, it looks like we're going to start here with carbon number 1 because we've got substituents right there. Our longest chain goes down here. So this is the last carbon in the chain. So we've got carbon number 1, 2, 3, 4, 5, 6, 7. So it looks like we've got heptane again. And on carbon number 3, we have an ethyl and a methyl. So this is 3 ethyl, 3 methyl heptane. All right, for the next, we're drawing 2 chair structure representations of the following compound. So I'm going to go ahead and draw a cyclohexane ring. When I draw this, I basically draw kind of a sideways V, and I make sure that my next 2 lines are parallel with each other. And then when I draw the next line, I make sure that line, so the line that I'm drawing right now, is parallel with this line right here. So that line there, and then I connect it, and I make sure that line here that I'm drawing now is parallel with that line there. All right, let me erase some of those notes. So there's my chair structure. And now I've got a methyl group at the 1 and 3 position, and they're both facing in the same way, out. So if it's on a wedge like this, it's facing out towards you, so coming out from the paper or the screen towards you, which means that on my ring, I'm going to make that face up. So on my chair structure, I'm going to say this is carbon number 1. I've got a methyl group in the up position rather than the down position. This is also the axial position. At a high point on the ring, your up positions are axial positions. So this is carbon number 1, this is carbon number 1, this is carbon number 2, this is carbon number 3. At carbon number 3, I also have a wedge, so that should be the up position. In this case, on carbon number 3, the up position is an axial position. So that's one representation. And for the second, we have also a chair structure. I'm just going to flip this. So I'm going to say carbon number 1 is going to get flipped down to here, and carbon number 3 is going to get flipped up to here. So when I flip the chair, now I've got, again, my V structure, two parallel lines. My next line that I draw is parallel to the one over here, and then I'm going to connect that back and make that line parallel with this one right here. So let me erase the bonds that I've circled for, oops. Let me erase my circle, not my bond line. Okay, let me just draw that again. All right, last time. So I can't make that straight up and down or else the axial positions won't make sense. So I gotta have a little bit of an angle to it. And then I've got two parallel lines that I'm gonna draw. All right, still not great, but it's fine. So when I flip this carbon 1 down, so this is now carbon number 1. The up position, so carbon number 1 is here, 2 is here, and 3 is there. For carbon number 1, the up position is now the equatorial position. And this bond that I've just drawn is parallel to the bond between carbon number 2 and carbon number 3. For carbon number 3, I'm going to go ahead and label this 4 and 5 because we'll talk about how I draw that bond too. For carbon number 3, I also want the methyl group in the up position. In this case, that is also equatorial, and that bond coming from carbon number 3 is parallel to the bond between carbon number 4 and carbon number 5 of the ring. So for the ring structure, one more little quick hint here. I like drawing the ring better this way. For some reason it's cleaner. Anyway, for the ring structure, an easy way to remember where axial and equatorial positions are at all the high points on the ring. So in this case, let's call this carbon 1, 2, 3, 4, 5, and 6. At all the high points and all the low points on the ring. So for the high points, you have 3 of those. Those have up axial whatever substituents attached. So in this case, let's just say we've got a cyclohexane ring, which means we've got hydrogens attached at the high points on the ring, and those are the up axial position. At the low points on the ring, so in this case, carbon number 6, carbon number 2, and carbon number 4, we've got more hydrogens attached if this is a cyclohexane ring, and those are our down axial positions. The equatorial positions are everywhere else. So let's do the up equatorial positions. Those are going to be at the carbon where the down axial hydrogens are. So for the up equatorial hydrogens, I'm going to draw this line out, and that line is going to be parallel. So that carbon-hydrogen bond is going to be parallel with carbon 2, 3 on this ring. And for my next up equatorial position, I have a hydrogen at carbon number 6, which is up equatorial. That bond is parallel to the 1,2 bond in the ring. And then finally, my last one is carbon number 2. That hydrogen is going to be parallel to the 1,6 bond in the ring, and that is also up equatorial. So now for my down equatorial positions, those are everywhere else. So I've got one there on carbon number 1, another down equatorial on carbon number 5, and another down equatorial on carbon number 3. So that's my chair structure. And again, for what I've drawn over here, I didn't draw those hydrogens in. You don't need to. Just the general rule for bond line structures, you don't need to draw those hydrogens in. All right, next, rank the following from lowest to highest in water solubility. So this is a little bit tricky, and there's nothing wrong with looking these up, especially at this point for where you're at. But with the hydrogen bonding potential of the carboxylic acid, you've got dipole-dipole effect, and you've got hydrogen bonding effect. So this is going to be the most water soluble. In fact, ethyl acetate, this carboxylic acid, acetic acid, is water soluble. So this dissolves in water. This is vinegar, and we know vinegar dissolves in water. So this is going to be the most water soluble. I probably said ethyl acetate earlier because I was thinking of this. So this has definitely some bond polarity. So we've got electron density moving towards our oxygens there and there. Since that has some polar regions in it, it is going to interact with polar solvents, and water is a polar solvent. So this ethyl acetate is going to be slightly more soluble because of its electron density poles, from what I've drawn, than the second most water, the next most water soluble one, which is this one. So this one is number 2. This one has some bond polarity as well. That's number 3, and then this one is going to be last. So just to make sure, rank the following from lowest to highest in water solubility. Yep, number 1 is the highest. Acetic acid is the most water soluble, and this is the lowest. This is the least water soluble compound. All right, now for boiling point. So for boiling point, we know the boiling point of water is 100, and there's no problem with looking these up. Water has hydrogen bonding potential, which is why this molecule is so small, but still has the highest boiling point. Acetic acid's a little bit higher, that's around 115. Again, there's nothing wrong with looking that up. It makes sense because it's heavier than water, but has about the same amount of hydrogen bonding potential with itself. So acetic acid is the second. So to lowest to highest boiling point. So highest boiling point is number 1. That's number 1. That is number 2. Now for these others, you may have to look these up. So if this was a test, I probably wouldn't give something that's this close. Hexanes actually has a fairly close boiling point to ethyl acetate. But the reason I put these on here, I think ethyl acetate's a little bit higher because, again, you have your dipole-dipole interactions. So you're pulling electron density that way, pulling electron density that way, pulling electron density that way. So this ethyl acetate can interact with itself. Even though it has a very similar molecular weight to hexanes, this one is probably going to be a little bit higher in boiling point. So then the next one, hexanes, this has no dipole-dipole moment interactions and no hydrogen bonding, obviously, and it's simply a lot heavier than propane. So 1, 2, 3 carbons, this is propane. This is much lighter than hexane, so that's going to be number 4, and that's going to be number 5. All right, next for the arrow pushing mechanism, it looks like we have a very weak base and an extremely strong acid. So we're going to take some electrons. Since we already have the conjugate acid drawn for us, so one of the resonance contributors for that conjugate acid is this, so it looks like that hydrogen gets attached to the oxygen. So we're going to show the arrow pushing mechanism where those electrons are going to attack that proton. These electrons will go to the oxygen to deprotonate our protonated acetone to form acetone. In this case, this is our conjugate base. This is our conjugate acid. This is our acid, which happens to be drawn on the arrow this time, which it's fine. And this is our base. All right, looking at the resonance contributors for this, so this has a couple resonance contributors. In general, if you have a negative charge on a molecule, you're going to start with your resonance contributor by moving that negative charge somewhere. Usually, if you stop there, you'd overfill the octet, so you probably need one more arrow for where to move that charge to. So in that case, our other resonance contributor is our essentially other alkene. If you have a positive charge, usually you only need to do one arrow at a time. So I'm going to move the electrons from this bond to this oxygen. I don't need to move anything else because the positive charge has to go somewhere else. We can just put it on this carbon rather than moving this double bond and skipping over an important resonance contributor. So we've got our alkene there attached to the ring. We've got our 6-membered ring, our hexane, our cyclohexane ring. That now is a single bond. We have an oxygen attached to a hydrogen. Now our oxygen has 2 lone pairs and it's neutral. Now the carbon that we took electrons from has a positive charge, and our alkene is still there. So for the next contributor, we can take electrons from this alkene and we can go bond to bond with our electron movement. That stabilizes that positive charge, and it takes electrons from this carbon right here. So drawing that other contributor, we still have our alkene there. We still have our 6-membered ring. We still have our alcohol functional group. And now we have our alkene right here. And now we have a positive charge on that carbon. So for the most stable resonance contributor, the most stable contributor of these is actually the first one. So this first one is the most stable resonance contributor. Oxygen in this case still has 4 things attached to it. So it still has the lone pair of electrons and 3 bonds. So in total it has 5 electrons, so it does still have that +1 charge, but it still has 4 things attached to it. These carbons, so this carbon here and this carbon here for our resonance contributors, only have 3 things attached to them. So they have a fully empty orbital. It's not just that it's missing electrons, it's missing electrons too, but it also has an empty orbital, making these 2 contributors significantly less stable. All right, and then finally for this, let's think about which side would be favored. So both of these are remarkably strong acids. Essentially, in both cases, we've protonated a ketone. However, with the positive charge, I would say that this one is probably a little bit more stable. So since we can stabilize that positive charge, I would guess that the reaction is going to favor the products just because the conjugate acid in this case is a little bit more stable. So if this protonated ketone has a pKa of -8, I'm going to guess that this protonated ketone, which is conjugated with an alkene, has a pKa of slightly less than that. So I'm going to guess the pKa of this is about -6. So again, in this case, the product side would be favored, even though these are remarkably close in terms of acidity. They're both our acid and our conjugate acid are very, very strong acids.